The 20th century saw humanity unlock the secrets of the atom, unleashing a power both awe-inspiring and terrifying. This monumental discovery marked a turning point in human history, forever altering the course of science and warfare. This power, harnessed in the form of nuclear weapons, has the capacity to level cities, poison landscapes, and end millions of lives in an instant. The sheer scale of destruction is almost unimaginable, leaving behind a legacy of fear and devastation. In the tapestry of human history, the creation of the nuclear bomb represents a profound and sobering chapter. It stands as a testament to human ingenuity and scientific prowess, yet also as a grim reminder of our potential for catastrophic destruction. It is a testament to our ingenuity, but also a stark reminder of our capacity for destruction. The duality of this invention reflects the complex nature of human progress. The very mention of a nuclear bomb conjures up images of apocalyptic destruction. Cities reduced to rubble, landscapes scarred by radiation, and countless lives lost in an instant. Mushroom clouds billowing into the sky, shockwaves flattening everything in their path, and a blinding flash of light that sears the earth. These haunting images are etched into our collective memory, but behind these terrifying images lies a fascinating and complex scientific process. The journey from theoretical physics to practical application is a story of relentless curiosity and determination. Understanding how these weapons work is not about glorifying their destructive power, but about comprehending the forces at play and the importance of preventing their use. Knowledge is our greatest tool in advocating for peace and disarmament. This essay aims to shed light on the science behind nuclear bombs. By exploring the intricate details, we can better appreciate the gravity of their existence. We will delve into the heart of the atom, exploring the concepts of nuclear fission and fusion. These fundamental processes are the building blocks of nuclear technology. We will examine the intricate mechanisms that trigger a nuclear detonation and discuss the devastating consequences of these weapons. The science behind the explosion is as fascinating as it is frightening. By understanding this technology, we can better grasp the gravity of its existence and advocate for its control. The knowledge empowers us to push for global disarmament and a safer world. Ultimately, the story of the nuclear bomb is not just a scientific one, but a human one. It is intertwined with the lives of those who created it, those who suffered its consequences, and those who strive to prevent its future use. It is a story about our potential for both progress and destruction, and the responsibility that comes with wielding such immense power. The duality of nuclear technology reflects the broader duality of human nature. It is a story that demands our attention, our understanding, and above all, our commitment to ensuring that these weapons are never used again. The future of humanity depends on our ability to learn from the past and strive for a peaceful world.
To understand the destructive power of a nuclear bomb, one must first delve into the heart of the atom, the very building block of matter, and grasp the concept of nuclear fission, a process that releases an immense amount of energy. Imagine an atom as a miniature solar system, with a dense nucleus at its core, orbited by tiny electrons, much like planets orbiting a sun. The nucleus itself is made up of even smaller particles called protons and neutrons, which are held together by strong nuclear forces. Fission, in its simplest terms, is the splitting of an atom's nucleus into smaller parts. Certain heavy elements like uranium and plutonium are naturally unstable and prone to fission. Their large, unwieldy nuclei are ripe for splitting, making them ideal candidates for fission reactions. When a neutron, a subatomic particle, strikes the nucleus of a uranium or plutonium atom with enough energy, it can cause the atom to become highly unstable and split. This instability leads to the nucleus splitting apart into two or more lighter atoms, releasing a tremendous amount of energy in the process, often in the form of heat and radiation. The energy released during fission comes from the conversion of a small amount of mass into energy, as described by Albert Einstein's famous equation, E equals mc squared, which fundamentally changed our understanding of physics. This simple equation reveals a profound truth: mass and energy are interchangeable, and even a tiny amount of mass can be converted into a colossal amount of energy, demonstrating the potential power locked within the atom. This process of nuclear fission is the driving force behind nuclear bombs, which harness this energy for destructive purposes. By triggering a chain reaction of fission events in a confined space, an immense amount of energy can be released in a fraction of a second, resulting in the devastating explosion we associate with these weapons, capable of causing widespread destruction. While fission forms the basis of most nuclear weapons, another even more powerful nuclear reaction can be harnessed: nuclear fusion. This process holds the potential for even greater energy release and has been a subject of intense scientific research. This is the process that powers the sun and other stars, and it involves fusing or combining atomic nuclei rather than splitting them. The energy produced by these celestial bodies is a testament to the immense power of fusion. In fusion reactions, light nuclei, such as those of hydrogen isotopes deuterium and tritium, are forced together under immense temperatures and pressures. These conditions are necessary to overcome the natural repulsive forces between the positively charged nuclei. Under these extreme conditions, the nuclei overcome their natural electrostatic repulsion and fuse, forming a heavier nucleus, such as helium. This process is accompanied by the release of a significant amount of energy. This fusion process also releases a tremendous amount of energy, even greater than that released in fission. The energy released in fusion is what makes it so appealing for both energy production and weaponry. In the sun, for example, hydrogen nuclei fuse to form helium, releasing the light and heat that sustain life on Earth. This natural fusion process has been occurring for billions of years, providing a continuous source of energy. Thermonuclear weapons, also known as hydrogen bombs, utilize fusion reactions to achieve their destructive power. These weapons are a stark reminder of the potential for both creation and destruction inherent in nuclear fusion. These weapons are significantly more powerful than traditional fission bombs and rely on a two-stage process. The first stage involves a fission reaction, which then triggers the fusion reaction. First, a fission reaction creates the extreme temperatures and pressures required for fusion. This initial explosion is crucial for setting the stage for the subsequent fusion reaction. This fission explosion then triggers the fusion of lighter nuclei, unleashing a secondary explosion of even greater magnitude. The combined energy release from both reactions results in a devastatingly powerful explosion. While both fission and fusion release enormous amounts of energy, fusion reactions are significantly more powerful. The energy output from fusion is what makes it a focus for future energy solutions and advanced weaponry. This difference in energy output stems from the fact that fusion reactions involve stronger nuclear forces and release a larger proportion of their mass as energy compared to fission reactions. The potential for harnessing this energy is immense. The development of thermonuclear weapons marked a significant escalation in the destructive potential of nuclear arsenals. This leap in technology has had profound implications for global security and the balance of power.
A nuclear bomb is a complex piece of engineering, but its basic components can be broken down into a few key elements. These components work together to initiate and sustain the nuclear chain reaction that leads to the devastating explosion. At the heart of a nuclear bomb lies the core, which contains the fissile material, typically highly enriched uranium or plutonium. This material is carefully shaped and arranged to achieve a critical mass when the bomb is detonated. Surrounding the core is the tamper, a dense layer of material, often made of uranium-238 or lead, that reflects neutrons back into the core, increasing the efficiency of the chain reaction. The initiator is a small device that triggers the nuclear explosion. It typically uses a conventional explosive to create a burst of neutrons that initiates the chain reaction in the core. Surrounding these core components is a complex array of high explosives carefully designed to compress the fissile material to a critical density. The precise arrangement and design of these components vary depending on the type of nuclear weapon. However, all nuclear bombs share these fundamental elements which work in concert to unleash the destructive power of the atom. Understanding the role of each component is crucial to comprehending the intricacies of nuclear weapon design and the devastating consequences of their use. So, the gun-type method is one of the earliest designs for nuclear bombs. It works by taking two subcritical masses of fissile material and shooting them together using a conventional explosive. When these masses combine, they form a supercritical mass, which then initiates a nuclear chain reaction. It's a relatively simple concept, but it requires precise engineering to ensure it works correctly. Now, the implosion method is a bit more complex. Instead of shooting two pieces together, this method uses a spherical arrangement of conventional explosives to compress a subcritical core of fissile material into a supercritical state. This compression increases the density of the material, making it capable of sustaining a nuclear chain reaction. It's a more efficient design and allows for a more compact bomb. But it also requires very precise timing and engineering to achieve the necessary compression.
The detonation process of a nuclear bomb is, well, a highly complex sequence of events. It all begins with the triggering mechanism, which sets off a chain reaction. This reaction causes the fissile material to reach a supercritical mass, leading to an explosive release of energy. The entire process happens in a matter of microseconds, making it almost instantaneous. When a nuclear bomb detonates, it produces an immense amount of heat and light. The temperature at the core of the explosion can reach millions of degrees, creating a fireball that expands rapidly. This intense heat can cause severe burns and ignite fires over a vast area. The light emitted is so bright that it can cause temporary or permanent blindness to anyone looking directly at the explosion. The explosion generates a massive shockwave, creating a sudden and extreme increase in pressure. This shockwave travels at supersonic speeds, causing widespread destruction. The force of the blast can flatten buildings and uproot trees. Following the initial shockwave, there is a powerful wind that can carry debris and cause additional damage over a large radius.
Radiation is often referred to as the invisible killer. After a nuclear explosion, radioactive particles are released into the atmosphere. These particles can cause severe health effects, including acute radiation sickness and long-term cancers. The fallout can contaminate air, water, and soil, posing a threat to life for years to come. It's a silent yet deadly consequence of nuclear warfare. Kindly like, share, and follow us for more.